So moving from ordinary thunderstorms to multicell thunderstorms, you just have to think of multicell thunderstorms as having many different ordinary thunderstorms in one place. So you will have several ordinary thunderstorms in different stages in one multicell thunderstorm. And the other difference is the level of wind shear that's associated with all of those ordinary thunderstorms grouped together. Remember, wind shear is a change in the vector of the wind, which means you are changing the speed of the wind or the direction of the wind or both. And in the case of multicell thunderstorms, you are changing both the speed and the direction. When I talk about multicell thunderstorms and that change, what I am saying is, let's go with the speed first. You still have some friction in the lower levels of the atmosphere, but because these storms are reaching up to the tropopause, they're hitting the jet stream up there. There's a huge difference between the 15-mile-an-hour wind that you find near the surface and the 250-mile-an-hour wind that you might find up in a polar jet stream, or a 70-mile-an-hour wind that you might find in a subtropical jet stream. So you can have dramatic changes in speed for wind shear, and that would cause wind shear all on its own. Then we're also going to explore changes in direction, because by some of the movement of this air, you're actually changing the direction of the air at the surface, which is leading you to some of the big issues with damage due to thunderstorms. And another thing to note about is that in the Great Plains, with those very flat areas, you have less friction in those areas. So it's very possible to change direction with some of these winds without the friction. And that's where you start to think about Tornado Alley. Let's go into it a little bit more so we can understand wind shear in here. When you have several cells collecting together, they do have a leading edge, and the leading edge is where your warm, moist air is going to come in and rise. When it rises and convects, it may meet the jet stream, which is going to take it on the prevailing westerlies and move it toward the east. And when you're also thinking about that, you also have a downdraft that has started in here because of the evaporation that is happening in the dry areas at the top of the atmosphere, cooling the air with the evaporation and starting this downdraft. Well, look at the direction of the winds in the middle of the atmosphere here, in the middle of the tropopause. They can just feed right in to your converging air. So now you have a rising slow, clouds and snow, surface low in here, and you have a sinking sky, warm and dry, well, it's certainly warm, and surface high. So you'll have a low in here, a surface low, a surface high. You'll have diverging air, and you'll have converging air. It sounds a lot like a cyclonic storm, doesn't it? And it has many of the same characteristics of the cyclonic storm, which is why we studied it first. When you look into that, that's what I wanted to point out to you here. You do have a cyclonic storm, which is working with converging and diverging air. And not only that, but you have a tilt that you noticed with the cyclonic storms in mid-latitudes. They have a backwards tilt due to the low that moves to the west and to the west when we get to the higher altitudes. Well, look what's happening here. We have a tilting storm here as well, and it is tilting to really supply that converging air in and to diverge that air off. Sorry, let me move this forward. There. Similar tilt back vertical schedule, vertical stand to it. Now, that leading edge is obviously where the new cells arrive in and continue the convecting process. And as we said, when you have a backdraft in here that feeds the high, that high can diverge out at the surface and can change some directions right along the surface, just adding to your wind shear in here, causing some really gusty winds. It'll prolong the storm as it does that, because you've got an updraft that is really very separate from the downdraft, and that those two can work independently of each other. You'll have a lot of rain out in the leading edge that will continue. You can get strong wind gusts with multicell thunderstorms. You can get hail from the circular rotation within them. Gust fronts can be very strong. We noticed one last week. They can produce shelf clouds right in back of the gust front. The gust front will come through, though you may see a shelf cloud. You may see roll clouds as well due to that wind shear. And what I wanted to point out to you is the gust front actually feels like a cold front when it comes through, but it is a gust front instead. And that is often associated with the straight line winds that come through that everybody thinks are tornadoes. They're often just a blast of a gust front. The one that came through last week caused a lot of damage. And those are straight line winds rather than rotating winds. So gust fronts can be quite dramatic, very short-lived, and they can feel like a cold front. Here is your gust front here. That is right behind your warm, moist air lifting. Then the downdraft comes right down. I wanted to point out a shelf cloud here that is right in back of a gust front that has come through. And you might say, well, why is this important? Yes, you're seeing that anvil up there for the very high cloud. This is a very flat cloud. And it's a very flat cloud because it has, I'm going to go back, it has the warm air just over it. Oh, I guess I have to go back here. It has the warm air just over it. So that warm air is acting as a lid on that shelf front, that shelf cloud that you have there. So very interesting to note that when you feel a gust front, if you look up, you'll often see a shelf cloud, very flat, very stable air above it, and then very unstable air back in the thunderstorm. You may see right in back of the shelf cloud, you may see a roll cloud, and those are very scary. They tend to, and we'll get into this a bit more, they tend to roll and have a horizontal axis to them. You can imagine that if this cloud was already rolling and it got an updraft underneath it, you'd have a tornado funnel right there. And that's a big part of what we're going to be looking into. So roll clouds can form. This is another, it's a combination. There's the shelf cloud of it, but you can see there's some rotation that might start soon right there. This brings me to the point where all this turbulence in this area, all this rotation in this area, lends itself to microbursts, which are so hazardous to air travel. And I wanted to point out to you that many crashes in the 50s, 60s, and 70s were before flights had computer algorithms to predict microbursts in front. And what would happen before those systems were in place is that the flight and the pilot would notice a headwind that was right underneath a massive cumulonimbus cloud. And if he has a headwind, or if she has a headwind in that area, the temptation is to tilt the nose downward, because suddenly this plane is taking off a lot faster and going up at a very good clip, which is alarming your passengers. So the tendency is to tilt the nose downward, and that is a fatal mistake, because within a few seconds you will get this straight down burst, which will take the plane down sometimes 100 meters or more, and then you will get the other side of this wind shear that is pushing the plane down. If you have a plane that also has its nose down and it's being pushed down by the microburst downdraft, it's going to head right into the ground. And this happened numerous times in the 50s, 60s, and 70s until they developed some in-flight algorithms to understand what was going on, and that you can never tilt the nose down during these circumstances. It's a rough ride, and you'll find that most pilots will steer very well clear of cumulonimbus clouds, but there's a way to get through them if you get caught in those microbursts. I also wanted to point out that those gust fronts can form their own cold front out in front. So while gust fronts can appear to be cold fronts, they will actually meet warm air out there and can form what's called an outflow boundary, which is like a very thin cold front out in front. When you have many multi-cell thunderstorms grouped together, they can form one of two things. They can form into one big grouping that tends to form into a circle, a mesocell convective complex. You might see it in the NOAA forecast discussions as an MCC, mesoscale convective complex. You will see these, and I put this in here from the GOES satellite feed. If you look at the GOES satellite feed on the geocolor around 8 p.m. Eastern Daylight Time, which is right around 4 p.m. out in Colorado, you will see these big circular, very, very fast-growing convective clouds, and you will know that those are mesoscale convective complexes. You'll see them just fly up at the end of the day, and those could definitely have tornadoes in them. They're usually seen at sunset around that convective line that we were talking about in Colorado. If they don't form mesoscale convective complexes, they might form a line of multi-cell thunderstorms, which is a squall line. These can be really devastating because that downdraft can actually start to pull in a subtropical jet stream and really cause a very, very powerful gust front and some really powerful backdrafts as well. So that's a squall line, which you notice here. There's the squall line. Here's the cold front. So the squall line tends to go out in front of the squall front, the cold front. We don't know a lot about squall lines. There's a lot of research that needs to be done. And in terms of thunder snow, you recognize that there is a warm air mass up above, and that is fueling that unstable atmosphere. That unstable atmosphere releases energy, and that release can be in the form of lightning and thunder. We'll get into this soon, and we're getting into supercell storms next, and onto tornadoes. Let's go for it.